All right, so in this video, we're going to talk about area, not volume anymore, but area by double integration. And so if you'll remember, we've got our volume set up from earlier in this chapter, volume equal to double integral over region R under the surface dA. And so when we think about this in its most fundamental form, this guy here we defined as the area component, and this was the height then. We talked about how we have these rectangular prisms now. We're going to find the volume of the rectangular prisms, and then we're going to add them all up. But now if we only want the area, it's really not going to be much of an adjustment. We can just say the area is going to be the double integral over region R with simply the dA. We're just removing that third component that would give us the volume. So the example I want to look at here is going to be the area bounded by, so again, area bounded by y equals x squared plus 1 and y equals 9 minus x squared. So when we sketch this region, which is, as always, a very important part of this process, we've got our parabola shifted up 1 unit that opens up. So that's going to be at 1. And then we've got our parabola shifted up 9 units, it opens down. So something like this. So we're looking for area here. Now, this really is not any different than it was in Calc 1, but we have to remember now, it's a double integral and then a dA. So to get this set up, are you going to go dy dx or dx dy? Well, I think it makes most sense to go vertically here. Because had we gone horizontally, we would have different rights and lefts there than we would here. So vertically makes more sense. Vertically means dy dx. So dy dx. And notice that's all that I have is dy dx. I'm not putting any kind of surface in there. This is an area computation. So then we know that this has to be a y equals and a y equals. And these have to be constants, x's. So the top would be the parabola that opens down, so that's going to be our 9 minus x squared. The bottom is going to be the parabola that opens up, which would be our x squared plus 1. And then we would need to scan from here over to here. To figure that stuff out, we would need to set both of these equal to one another and find the points of intersection. So that would be x squared plus 1 set equal to 9 minus x squared, which is going to be 2x squared equals 8, x squared equals 4, so x equals plus or minus 2. So this guy here would be negative 2, and this guy here would be positive 2. Now, for volume, you can use symmetry from time to time, but you have to be very careful because even though your region R might be symmetric, what's happening above it might not be. But for area, it's very obvious that this particular one, symmetry is a great option. So I'll go ahead and throw a 2 out in front of this. And let's just say now we're going to go from 0 to 2. You certainly could have gone negative 2 to 2 and excluded that, but again, symmetry is a nice tool if possible. An area, we know we're safe. So there's our setup. Now, I do want to carry this down one additional step here. The step that I would do next would keep my 0 to 2, and then since we're integrating with respect to y, then the only thing that happens is that this y pops up, needing to be evaluated at x squared plus 1 and 9 minus x squared dx. And so when I now evaluate, I've got my 9 minus x squared plugged in there minus the x squared plus 1 dx. And what I'm hoping you're seeing now is that this is the exact Calc 1 setup for area between these two curves. It was that top minus bottom from Calc 1, and that's exactly what we have here, top minus bottom. And so even though we're using a double integral to do this, it's again the exact same thing as we saw in Calc 1, only now we're using the double integral kind of as a guide to set this stuff up. I'm not going to work the rest of this out. It's a Calc 1 integral, but still a very, very interesting idea taking us back from volume into area.